would be great if like every section is right. I mean, you'll see one thing in Felder Rousseau and a different thing in the Harriet and a different thing in
Terrified of homework.
what
do you think here? Axial answers? I don't know. I really should study though. I don't know what I should study.
Yep. You want to take 2 minutes?
You want me to look at your resume? Yeah.
All right, let's get started. First, any questions? Okay, the homeworks are due before class or at the beginning of class. All right, so it's fine if you leave them up here. You can also leave them in my mailbox or right by my office door. There's a little thing where you can drop them. Okay, but let's get them all in before class. Last time the graders got a few late because you guys turned them in pretty late. But I said you could last time. This time before class. So when we last left, we were working through an example, and we're going to continue that example to start class today. So I had put most of this stoichiometric table on the board. I think I left out this change column. But if you don't have this in your notes or something close to it, then go ahead and get that down. And remember that our goal within this chapter, which this chapter is called stoichiometry, nice and vague. But the goal is what, right? It's to get concentrations of species now written as a function of what? Conversion. And that's because we want rate as a function of conversion, right? That's in your homeworks. That's how we make the Levenspiel plot. Now in your homeworks, you've just been told how the rate, or in some instances, it'll just tell you 1 over the rate. But they'll just tell you how it changes with conversion. Well, things aren't usually so simple, right? So this is what we want. And so to do that, remember that we have from chapter 3 and 9 was all about getting the concentration, the rate as a function of concentrations. And so now if we can get concentrations as a function of conversion, then we can use that inside here to ultimately get rates as a function of conversion. Okay? And because you might have a flowing system versus a static system, you might have something where there's pressure change, where there's no pressure change, isothermal, temperature change. This is not trivial, right? Because the volume can be changing, or the volumetric flow rate, also as a function of conversion. So that's what led to really everything that we talked about in the last lecture and that we're going to finish with today. Because since that volume can change, the concentration changes are not trivial to get. It's pretty trivial to write the number of moles or the flow rates as a function of conversion. We did that in half a class. But it's getting it in terms of concentrations that's tricky. And that's again because the volumes might be changing, the volumetric flow rates might be changing. Okay, so just continuing where we left off. Some of this I might have had on the board, but I'd rather be a little bit repetitive than skip a section. So we have concentration of a species, the flow rate of that species divided by the volumetric flow rate. And remember that we've already derived the formula for the volumetric flow rate as a function of conversion. Now at the beginning of this problem, did we say that it was an isothermal reactor? Yes. So this goes to 1. Did we say that we could neglect pressure drop? Yes. So this also goes to 1. So we're left with a rather simple expression for how the volumetric flow rate changes with conversion. Of course, a big reason why it looks simple is because we defined a variable to make it look simple, right? That's why that epsilon variable exists, just to make this look simple. And so if we write that out for the individual species, so here's the flow rates of A, B, C, D, or A, B, C, and I for the inert. But what we really want, right, are the concentrations. So let's write that out for each one, and then we're going to continue the problem. So we get FAO times 1 minus X divided by, so all I've done here is take FA, right? Now I'm dividing by the volumetric flow rate, which is V naught times 1 plus epsilon times conversion. And I can rewrite this because we call this grouping of terms right here just the initial concentration. Okay? So that's the flow rate divided by the volume. So we still have those conversion terms left in here. So 1 minus conversion divided by 1 plus epsilon times conversion. So any questions? All I did was take FA, which I defined over here in the stoichiometric table, and I divided by the volumetric flow rate, and we had already developed the equation for how volumetric flow rate changes with conversion for an isothermal system in which we can neglect pressure drop. So CB is simply the initial concentration of A times now that big theta minus 1/2 X divided by the 1 plus epsilon X. And that big theta B is just equal to 0.54. So in one case, I put the symbol just to remind you of it. Here we had the number. Okay, and then the concentration of C is CaO X 1 plus epsilon X. It's just FaO X, right? So now it's just CaO X. Finally, we have one more concentration term that we can define. Even though it doesn't show up in our rate equations, a lot of times it's still useful to define the concentration of the inert. CaO I know that might be hard to read. That's just 1 plus epsilon x. It's the same denominator in all cases. So let's get CaO. That's just equal to the mole fraction of A at the inlet times what? The total concentration of species. So what is the total concentration of species for an ideal gas? We get it from PV equals nRT. Recall that this would be N over V, right? So what you're left with is P naught over R T naught. Okay? But yeah, that's from the ideal gas law. PV equals nRT, and concentration is just N over V. So putting that back into here, we get YA naught times P naught divided by R T naught. And we can actually solve that out based on the numbers that I gave you. You have all the information that you need. I gave you a temperature, I gave you a pressure, and we know that the initial mole fraction was specified as well. And so you get 0.28 I cannot read it right. 1485 0.1 moles per decimeter cubed. So my notes are lazy about units, so I'm being lazy about units, but let me strongly recommend against you doing this on a test. If you do this, I promise you there's going to be a unit conversion that you're missing. Because I'm not the kind of guy that's just going to let all the units cancel out because I'm so nice. It won't be a lot of unit conversions, but occasionally we're going to have them, just to remind you that they exist in reality. So I mean, I recommend doing that like train track method that you guys hopefully learned at some point in probably material and energy balances so many years ago that you guys have forgotten. Okay, but that'll help you make sure that the units are correct. If the units give you concentrations at the end, you're usually in good shape, right? Otherwise, you might have left out something like the pressure or the temperature, and suddenly the units won't work. It's because you grabbed the wrong formula.
We have to know them by heart.
Unit conversions?
Yeah.
No. Any unit conversions you need will be given. You might get more than you need, but they'll be given. I'm not going to hand you Perry's and say good luck, but I'll probably have a sheet that has many common unit conversions in it. It'll probably be the front page, I think, one of the yellow books. Or is it Felder and Rousseau? Has that first, like the inside cover is a bunch of unit conversions?
I think it's the MEV one.
All right, one of them has it. Yeah, Felder and Rousseau, that's MEV. Okay, what's epsilon equal to? Delta times YA naught. So delta, I won't ask you guys because it was on the board a long time ago. 1 minus a half minus 1. And that's because, and then times 0.28. So epsilon is equal to minus 0.14. And so finally we can write out those same concentrations now. We'll put numbers there. 0.1 times 1 minus x, 1 minus 0.14 times x. is the flow rate of an inert dependent upon the extent of conversion? No. Flow rates are not. Concentrations are. Okay? So yeah, when we wrote out our stoichiometric table for change in flow rate, we just put nothing for the inert. Isn't that great? That's so useful. Inerts don't react. Unfortunately, for concentrations, their concentrations can still change. And why is that? Not because the rest of them are changing, it's because the volumetric flow rate is changing. Right? Remember, concentration, F over V. So it's because the volumetric flow rate is changing, which is, of course, related to all the, what the other species are doing. All right, so now we have expressions for concentrations in terms of conversions, right? So what do we do with that? Are we done?
No.
Do we add them all up?
We don't add them. Why would we want to add them? What does that tell us?
I don't know, I thought you added them all.
I think somebody said it.
It'll be equal to 1.
Yeah, we want to put them into the rate equations. Remember that in order to size a reactor, we have to know how the rate changes with conversion. That's what we did 2 weeks ago. I don't know when we started it. That's what your homework is about. But again, in your homeworks, you've been told how does conversion change with rate. This is the only homework where you're going to be told that. Okay? The rest of the time, that's the whole point of this class, is to do that exact exercise so that you can size the reactor. Okay, so for example, that could be our rate equation, right? It's not guaranteed that that's your rate equation. That's not always going to be your rate equation. That's what we started the class with, was how do you develop those rate equations. But now that you know how to develop the rate equation, you write out the rate, and so now we can continue it, right? We can say K times now what's CA? Just that mess over there. CAO, 1 minus X, 1 plus epsilon X.
Should that R have an
Should the R have an A? Yeah, I'm writing the rate of consumption of it. When we wrote out rate equations, you could either write them for a step, but often we would also write them for a species. And remember that we use A because the first thing we did was find out which was our limiting reagent, and we decided conversion would be in terms of that limiting reagent, and that was A. So that's why we're writing rate of A, not rate of B. Okay. CAO, big theta, B over A, X. So under what conditions is this true? You see that I put the symbols back in, right? So when is this true? It's true for an isothermal reaction? Right. Otherwise, if it wasn't isothermal, I'd have to have some temperature terms in the denominator. Is this true for a system where there's pressure drop? No. Once again, there'd be terms up there related to the change in pressure. So this is true for a flow system in which we have an isothermal system where we can neglect pressure drop. Then